So this example is going to illustrate the short circuit ratio ramping test. It's an informational test defined in P2000.2. That's draft D0.5. What happens is we start with a source that's fairly strong. So here I've changed this voltage source, so it's got essentially zero impedance. It's just an ideal voltage source, and I put in a very small reactance here of 0.003 ohms. So this is the strongest the grid can be. Now we still have inductive elements inside the plant. In here, we've got the park transformer and the inverter transformers. So that adds significant inductance. So that, from the standpoint of the voltage source converter, there's still a significant, short circuit ratio. But in order to get transitions between these different short circuit values, we put a three-phase fault at different times at 5-second intervals. So that's these faults here numbered from 1 to 7. So if I look at one of these, the fault applied at 10 seconds and cleared at 10.16 seconds. So the plant should ride through. And the fault impedance is very low. So it's basically a volted fault. I'm gonna hit cancel there. So when that happens, initially notice that this switch number 1 here is closed, so it puts this low impedance in the fault. So I'm going to open this, I don't know if you can see that, at 10.08 seconds. So this is halfway through the fault duration. So that fault is going to open at 10.16. While this is happening, while the fault is on, that switch is going to open, and then this one is going to close. So you notice switch 2 is closed. Excuse me, it's open. It's open. And I'm going to close it at 10.08 seconds. So it's commutating the current from RL1 to RL2. And that RL2 is only going to be in the circuit for 5 seconds because it's going to open at 15.08, and so that's when the next fault is applied. So what will happen is the current from this source, so you would see current spikes if you plotted RL1 and RL2 because you're switching currents from one inductor to another. But the IBR is kind of shielded from that transition because it's got this volted fault right here while that's happening. So after 10 seconds, we switch from RL1 to RL2. And then remember that RL2, the switch 2 opens at 15.08 seconds. And that's in the middle of the time that fault 2 is on the circuit. So fault 2 is applied at 15 seconds, cleared at 15.16. And then in the middle of that time, switch 2 here opens at 15.08. And switch 3 is closing at 15.08, and then it's going to open again 5 seconds later. So there are 7 transitions at 5-second intervals between the faults numbered, from 1 to 7 consecutively. We do not use JavaScript to automate this, so it's one simulation that's got a sequence of events, and we're not using the control reference input pins. This is the average model. It's under voltage control, so it's set to regulate the voltage at the bus to 1 per unit. So I would just click the simulate run button to run that case. When I've done that, I can go back to the Jupyter Notebook, see plot 6, and I will just run the cells to do the service functions, import matplotlib. We're going to run this cell to configure EMTP import, and we're going to read the data channel. So that's done, and then I'm going to plot the results. So these are voltage and current in the time domain, the first two plots. The RMS voltage estimated as, so you can see the successive faults at 5-second intervals, and each time the IBR comes back into service, it sees a higher source inductance. So it recovers from 3 of those events. So here at 10 seconds and at 15 seconds and at 20 seconds it comes back, but the fault at 25 seconds, when it comes back, the short circuit ratio is too low, so the power output is 0. So this is an informational test. It didn't, it was stable down to a pretty low short circuit ratio. So in fact, right in this range here, the short circuit ratio was 3. And when it went down to 2.5, that the plant did not come back. So this is a more severe scenario where we're having this faults occurring in between each transition.